Okay, so this is the first in a series of videos on our Year 10 trigonometry topic. The first half of the topic will be looking at right-angled trigonometry, much of which you will have seen previously in Year 9 maths. And then the second half of the topic will be heading into some non-right-angled trigonometry, or trigonometry in non-right-angled triangles, I should say, which will be new to you at this point. Now, obviously, throughout the trigonometry topic, we're going to need access to our calculator, so it's really important that you've got your calculator with you. Ideally, I want you to get used to using your CAS calculator as well, so please make sure that you've got your CAS with you. Okay, so before we get into any trigonometry, we need to understand a couple of things about our CAS, or else we're going to get ourselves in a bit of a knot. The first in particular is about the angle mode of our CAS. So just like we have different scales of measurement, we could measure a length in centimetres or inches. Okay, we could talk about centimetres versus metres, but they're really the same scale of measurement, it's just a different unit. Okay, what we're looking at here is a completely different scale, so centimetres versus inches, completely different sort of way of counting the measure, but they're both ways of counting length. Okay. Similarly, we have more than one way of measuring angles. Okay, we're all familiar with the idea of measuring an angle in degrees, but there's another way of measuring. Well, there's a couple of others, but in particular, in the next couple of years, we'll learn about another way of measuring angles, which is called radian measure. Okay, and actually, from year 11 onwards, you'll really only talk about angles using radian measure. Okay. But for now, we're going to stick with degrees. However, it means that we need to be a bit careful about the mode that our CAS is in. Now, mine's actually in the right mode here, but the default mode for your CAS, your default angle mode is radians. Okay, and you can actually see the current angle mode of your CAS by looking in the top right hand corner of the screen, where I can see that my CAS is in degree mode. I can see this little deg written here, and when I hover my cursor over this region, I actually see the word degree come up. So I'm in degree mode, okay? So that's fine. Your CAS might say rad, R-A-D up here, suggesting that it's in radian mode, okay? In which case, you're going to want to know how to change that. So if we're in the wrong mode, we're going to want to go up here in the scratch pad, or in document mode as well, but I encourage you to work in the scratch pad in this course. We don't need to do anything more than calculations and graphing, and I think it's easier for you to keep things neat and tidy in your scratch pad. So we're going to hover up over to the battery. The same instructions will work in your document though. We're going to click on the battery, okay, and then we're going to choose number 2, document settings. And then you'll see the second option here is angle mode, okay. And so you're going to want to make sure that you are in degree mode. If you were in radian mode, you want to change it to degree mode, and then tabbing down to the bottom here and pressing OK. Okay. It's really important that you know how to do that. Okay. You might well lend your CAS to your older brother while he does, you know, a maths methods test or something, and you'll get it back to you, and it'll be in radian mode, not in degree mode anymore. Okay, you might borrow a friend's and it's in the wrong mode. You might reset your CAS for some reason because something went wrong, or it went into a spin, or it got jammed, and so it might be in radian mode. It's really important that you know how to do this, and that you understand that as a step in terms of your troubleshooting. If you get an answer to a question that you think, that doesn't make any sense, that's one of the first things you want to be thinking about when you're doing trigonometry. Oh, hang on, is my CAS in the right angle mode? Okay, so we want to make sure that we're in degree mode. The second thing is, obviously, we're going to need to know where our trig ratios are. We'll use these over the next few lessons, but just while we're here talking about our CAS in particular, there's a special button labelled trig right next to the number 7, and when you press that, you'll get these 12 different options. Okay. Now, at the moment, and really, unless you do specialist maths, we're only going to be interested in the 6 options on the left-hand side there. Sine, cosine and tangent, and inverse sine, inverse cosine, and inverse tangent. Okay, so we'll leave them there for now. Again, remembering that my CAS gives exact answers if it can, and in trigonometry, sometimes the exact answers can look a bit scary, but if we're wanting our answer as a decimal, we simply just press Control-Enter instead of Enter to get our answer as a decimal. Okay, so when we're working with right-angled triangles, it's important to be able to name the side lengths relative to the angle that we're interested in. So if theta, so this angle down here, is the angle of interest, so I'll just bring that CAS back in case we need it. If theta, so the angle in the bottom left here, is the angle that we're interested in, then all the other sides are named relative to theta. Okay, except I should say for the hypotenuse. The hypotenuse is the same no matter which angle we're interested in. The hypotenuse, which we should be familiar with from our Pythagoras' theorem work, hypotenuse is always the longest side in a right-angled triangle. Okay, in any triangle, the longest side will be the side opposite the biggest angle. Okay, if you have a triangle, whether it's right-angled or not, where you have, say for example, this triangle here. Okay, possibly should make it slightly less right angle, even more extreme. This is clearly the biggest angle here, and because those two sides are then opening out the widest, the side that creates opposite is going to be the longest side. Okay, so biggest angle, opposite side will be the longest side. So therefore, in a right-angled triangle, because the angles in every triangle add up to 180 degrees, in a right-angled triangle, one of our angles is 90. Okay, which means that the other two angles have to be less than 90. So therefore the 90-degree angle is always the biggest angle in a triangle. And so that means the side length opposite the 90-degree angle is always the hypotenuse. Okay, so hypotenuse, longest side, side opposite the 90-degree angle. Then the other two side lengths depend on the angle we're interested in. So if we're interested in this angle down the bottom left here, then the opposite side length is the one opposite that angle. It's very straightforward. And adjacent means next to, so the adjacent side is the side next to the angle that we're interested in. If we change the situation and we were interested in this angle up here instead, alpha, now this becomes the opposite side and this becomes the adjacent side. Okay, so it's really important that we're able to name and label the sides accurately depending on what we're trying to find. We'll also notice that quite often we use Greek letters such as theta, alpha, beta and gamma to represent angles, where we tend to use Roman letters to represent corners of triangles or side lengths, etc, etc. So don't freak out if you see those symbols. That's fine, there's no test on what they're called, but you should be familiar with those basic Greek letters. Okay, so picture below we have three right-angled triangles. Okay, we want to think about, well, what could we say about these particular triangles? Now, we haven't revised this concept yet this year, but you should recall from year 9 that we do quite a bit of work about triangles, and in particular, the one thing I'm noticing about these three triangles is, whilst they're in different orientations and they have different side lengths, the thing that's the same about them is that they have the same angles. They have the same angles, okay, but they have different lengths. So they're enlargements of each other. Okay, we have a special word for this. We talk about them being, so this means we have similar triangles. Similar triangles, same shape, that's defined by the angles, but different size. Okay, if the angles are the same though, it means that all the side lengths have to be increased in the same proportion. Okay, so for example, going from triangle A to B, the side length 1 became this side length up here, 1.5. So all the side lengths in this triangle have to be 1.5 times. All the side lengths in triangle B have to be 1.5 times the side lengths in triangle A. Okay, this 2 times 1.5 is 3. Root 3 times 1.5 is 3 on 2 times root 3. Okay, and obviously we could see the same is true from A to C. We've doubled. Okay, this length is doubled, this length is doubled, and this length is doubled. If we simplify this third, we get that's the square root of 4 times 3, and so we get 2 root 3, which is indeed double. Okay, so we've got same angles, different side lengths all increased in the same proportion, and so therefore we have similar triangles. Alright, so for each of the above, we want to calculate the following using 30 degrees as the reference angle. Okay, so 30 degrees is the reference, which makes this the opposite, and this one the adjacent, and this one the hypotenuse. Over here, 30 degrees is my reference angle. This is therefore my opposite side. This is my hypotenuse, my longest side, and this is my adjacent side. Here, 30 degrees is my reference angle. Therefore, this is my opposite. This is my hypotenuse up here, and this is my adjacent. Adjacent. I might write this as, what was this? 2 root 3. Just simplify that. Okay, so for each of the above, we want to calculate the following using 30 degrees as the reference angle. Okay, so we want to do the opposite length divided by the hypotenuse. So in triangle A, that's going to be 1 divided by 2. In triangle B, okay, that's going to be a bit uglier, so it's going to be, I'm going to write out some steps here. We can use our CAS to help us, but we should be able to do this. 3 on 2 divided by 3, which means it is 3 on 2 times a third, which means our 3's are going to cancel out, and it is also 1/2. Okay. If we did opposite divided by hypotenuse for triangle C, so opposite side is 2, hypotenuse is 4, so we also get 1/2. So regardless of the size of the triangle, the opposite over hypotenuse when we're talking about the 30-degree angle is the same for all three triangles. If we were to again use the 30-degree reference angle, this time doing adjacent divided by hypotenuse, so in triangle A, that will be √3 over 2. In triangle B, okay, that will be, now we're going to need again some steps here because we've got some fractions, 3√3 on 2 divided by hypotenuse is 3. So remembering, that's times by a third. The 3's are going to cancel, and so we get √3 on 2. And then triangle C, again, adjacent over hypotenuse, so that is going to be 2√3 over hypotenuse is 4. 2 and 4 will cancel down to be 1√3 over 2, so √3 over 2. So again, we're seeing we get the same thing, okay? So we're seeing opposite over hypotenuse for all three triangles was 1/2. Adjacent over hypotenuse for all three triangles was √3 on 2. And if we have a look at opposite over adjacent, in triangle A, we've got 1 over √3. In triangle B, we're going to have 3 on 2 divided by √3 on 2. So that is 3 on 2 multiplied by 2 on 3√3. Our 3's are going to cancel down. Our 2's are also going to cancel down. So we've got 1 on √3 again. And triangle C, opposite over adjacent, is going to be 2 over √12 or 2 over 2√3. And so that is also 1 on √3. So again, here we have opposite over adjacent for all three triangles gives the same value. That's also to do with their similarity. Side lengths are in the same proportion. Okay, so if we divide the same pairs of side lengths in each of the three triangles, we should get the same value. Now, sorry, let's get rid of that. If we use our CAS and in degree mode to work out what sine of 30 degrees is, cos of 30 degrees, and tan of 30 degrees. Now, we don't need to enter the degree symbol. The fact that our CAS is in degree mode means that when we put a number inside the sine function, it will understand that that number is in degrees. Okay, that's why the degree mode is really important. All right, so sine of 30, so trig, choosing sine 30. I'm not going to press Control Enter here. I'm going to keep these nice exact values. So this is 1/2. Cos of 30. So trig button again, choosing cos of 30. √3 over 2. And tan of 30. Is √3 on 3. Now that's interesting because that's not quite what we got. But if we think about our answer didn't have a rational denominator. So if I multiply the numerator and denominator here by √3, I get 3 on 3√3, which is 1 on √3. So it's the same thing. Okay. So what we're seeing here is that regardless of the lengths of the sides, sine of 30 degrees is equal to the opposite side length divided by the hypotenuse side length, where we have a right-angled triangle with a 30-degree angle. Cos of 30 degrees is always equal to the adjacent length divided by the hypotenuse length, and tan of 30 degrees is always equal to the opposite length divided by the adjacent length, obviously in a triangle with 30 degrees. So if we were to do the same thing using the 60-degree reference angle, okay, so this time, I'm going to have to scroll up and down a bit here. So this time, let's change what's happening here. So this time we are interested in 60 degrees as the reference. Okay, So that changes. Our hypotenuse will still remain the longest side, or the side opposite the 90 degrees, but it will change which is adjacent, which is hypotenuse. So this becomes adjacent, this becomes opposite, this one becomes adjacent up the top here, this becomes opposite, and this becomes opposite, and this one's adjacent. Again, let's write this as, what did we say this one was? 2 root 3. Okay, so if we do the 60-degree angle, opposite over hypotenuse for the 3 triangles, opposite over hypotenuse in triangle A is root 3 on 2. Opposite over hypotenuse in triangle B is 3 root 3 on 2 divided by 3 on 2. Now we already did this calculation in the previous table, and it turned out to also be root 3 on 2. And in the triangle C, opposite over hypotenuse, 2 root 3 over 4. Again, we've got that common factor of 2, so we get root 3 over 2. And so we get the same values here. Adjacent over hypotenuse, in triangle A, it's 1 over 2. In triangle B, adjacent over hypotenuse is root 3 on 2 divided by, sorry, not root 3 on 2, is 3 on 2 divided by 3. Which also gives us half. Again, we did that calculation in the previous table. And adjacent over hypotenuse for triangle C is 2 over 4, which will simplify to 1/2. Opposite over adjacent in triangle A is root 3 over 1. So that's just root 3. In triangle B, opposite over adjacent, 3 root 3 on 2 divided by 3 on 2. Okay, so that's 3 root 3 on 2 times 2 on 3. So our 2's will cancel, our 3's will cancel, and we've just got root 3 on 1, so just root 3. And opposite over adjacent for triangle C is 2 root 3 over 2. So again, also just root 3. Okay, so again, we've got the same thing. Opposite over hypotenuse, when the 60-degree angle is what we're interested in, is always root 3 over 2. Adjacent over hypotenuse, when it's a 60-degree angle we're interested in, is always half. And opposite over adjacent is always root 3. Again, if we get our CAS to work out what is sine of 60. So sine of 60, it's root 3 on 2. Cos of 60, that's half. And tan of 60, it's root 3. So we see actually that sine of 60 degrees is equal to the opposite side length divided by the hypotenuse side length when we're using 60 degrees as the reference angle. Cos of 60 degrees is equal to the adjacent side divided by the hypotenuse, and tan of 60 degrees is equal to the opposite side divided by the adjacent. Okay, so what we're seeing here is that the ratios of the side lengths, this is what the trig functions are. They're actually called trig ratios, trigonometric ratios. Okay, the sine ratio is when you take, a ratio is a division. The sine ratio is when you take the opposite side length and divide it by the hypotenuse length. Okay, but we see the key thing is if we have a right angled triangle with a fixed angle, so sine of 30 degrees, for example, the opposite length divided by the hypotenuse length in all right angled triangles with a 30-degree angle will be the same. And that's because all of those triangles are similar triangles. Okay. So the ratios of the side lengths of right angled triangles are always equal as long as the angles are equal, and the value of each of the ratios is dependent on the angle. And so we can define the ratio in terms of that angle. We have special names for these ratios: sine, cosine, and tangent. And we use a 3-letter abbreviation just so we don't have to write sine, cosine, and tangent out every time, which we abbreviate. Now we don't say sin because it's an abbreviation for sine. We still describe it as sine. The abbreviation for cosine is cos, okay, and the abbreviation for tangent is tan. Okay, so sine of an angle is equal to the opposite length divided by the hypotenuse length. Cos of an angle is equal to the adjacent length divided by the hypotenuse length, and tan of an angle is equal to opposite length divided by the adjacent length. Okay, it's really important that sine and cos and tan don't exist on their own. It is sine of the angle. What is the opposite side divided by the hypotenuse side if I'm talking about this particular angle? Okay, you can't ever just write sine equals such and such. Sine of an angle will be equal to something. Okay, so hopefully this is a fairly familiar sort of acronym. SOHCAHTOA, sine opposite hypotenuse, cos adjacent hypotenuse, tan opposite adjacent. Okay, SOHCAHTOA enables us to remember those things. These are things you're going to need to recall, so if this isn't that familiar, it's important that you kind of get used to that. Okay, so let's have a look at the triangle below and use it to find each of the following correct to two decimal places. So we want to know what sine of 20 degrees is. Okay, so 20 is our reference angle. Okay, sine we know is about opposite divided by hypotenuse. Now obviously the opposite length depends on the angle. So if we're talking about the 20-degree angle, this is the opposite length, and the hypotenuse obviously is the longest length, so this one up here. Okay, so in this case opposite is 4.368, and we're going to divide that by the hypotenuse, which is 12.770, and so to two decimal places, 4.368 divided by 12.770, it is about 0.34. That doesn't have any units, that's a ratio. That is, what ratio do you get when you divide this length by this length? Okay, what we're seeing here is that the opposite length is about 34% of the hypotenuse length. That's essentially what we're looking at here, a ratio, a comparison of those two side lengths. Okay, if we want cos of 20 degrees, so this time we're going to need to make use of the adjacent length, which will be 12. Okay, so cos of 20 degrees, remember cos being adjacent over hypotenuse. Okay, so in this case the adjacent length is 12, the hypotenuse is 12.770. Okay, and then two decimal places, get our calcs to do that, 12 divided by, it's about 0.94. Okay, again that's a ratio, it hasn't got any units. Okay, that is about what proportion is the adjacent side compared to the hypotenuse side. Okay, so the adjacent side length is about 94% of the hypotenuse side length. Okay, sine of 70 degrees. Okay, so let's switch things around. This time we're interested in the 70-degree angle. Okay, so if we've got a right angle triangle with, we know 90 degrees is already taken, 20 degrees up here, it means this angle up the top here must be 90 minus 20, so it must be 70 degrees. Okay, so therefore that makes 12 the opposite of 70. It makes 4.368 the adjacent side, and 12.770 remains the hypotenuse. So sine of 70, opposite over hypotenuse. So in this instance that is 12 over 12.770. We actually did that calculation in the previous example, so 0.94. So again, we're seeing that the opposite side length, 12, is about 94% of the hypotenuse side length, 12.770. Tan of 70 degrees, so tan is opposite over adjacent. Okay, so tan of 70 degrees, opposite is 12, adjacent is 4.368. Okay. So in this case, the opposite side length is bigger than the adjacent side length. So we're going to get a number bigger than 1 here. So 12 divided by 4.368. 2.75. So two decimal places. Okay, so again, this time we're seeing that the opposite side length is about 2.75 times the adjacent side length. Okay, it's a proportion comparing the two side lengths. Okay, and we just give it a special name called tangent, a special name called sine, and a special name called cosine. We'll have a bit of a look a little later on, just very briefly, just a slight taste of where these definitions of sine and cosine and tangent actually come from. They have a bigger definition than being able to be used in right angled triangles. So we actually learn trigonometry a bit backwards. We learn it from the midway point where we learn how to use sine, cosine and tangent, and then in year 11 we go back and get an understanding of actually where sine, cosine and tangent begin from and how that can then be used in right angled triangles. But for now we need to take a little bit as given, and we'll come back to that later. We will have a small look at that. We'll look at the unit circle very briefly in a couple of lessons' time. Okay, so I want you to have a play around today with just getting a sense of what is sine and cosine and tangent about and how do we calculate them. So I want to be clear, in these examples we've just done here, we're not trying to work out what the angle is, we're not trying to work out what the side length is, we're just getting familiar with these relationships that sine is the opposite side length divided by the hypotenuse length, etc., etc. We should be able to confirm, if I just quickly before I finish, if I type sine of 20 degrees into my calculator here and press Control Enter to get a decimal, it is about 0.34. Okay, obviously we've got some approximate decimals here, we've done a little bit of rounding. But that's true for all right angled triangles with a 20 degree angle. Again, cosine of 20 should match what we found in part B there. To 2 decimal places, yeah, it's 0.94. Okay, sine of 70 degrees should be the same. Yeah, 0.94, and tan of 70 degrees, 2.75. Oh, sorry, not 2.75, tan of 70 degrees. Sorry, put the length in there, always putting the angle inside the tan function. Sorry, let's get rid of that, and let's press, apologies, let's get rid of that one, and let's actually press Control Enter here to get this one as a decimal. So yes, 2.75, matching what we're seeing there. Okay. The point here is not to actually just type 2 sine of 20 into your calculator. The point is to get an understanding of which two side lengths are we finding the ratio of. What is the definition of sine and how do we use that? Okay. So working your way through this worksheet for today's work.